Welcome back. Very often, we want to concentrate the enhancement of an image at its edges. We want to leave the rest of the image unchanged, but only make the edges look sharper. A sharpened image typically conveys more information, more details to the human viewer. Therefore, such class of enhancement techniques is referred to as sharpening techniques. This is the topic of this segment, in which we'll describe a number of such sharpening techniques. We will start with unsharp masking or high boost filtering. The idea is very straightforward and has its roots in analog photography. A blurred version of the image is formed, the unsharp mask, which when subtracted from the original image will provide the high frequency information of the image. If this information, typically amplified, is added to the original image, a sharpened image results. Of course, any high-pass filter can extract such high-frequency information from an image. An example of such a high-pass filter is the Laplacian. We'll talk about the Laplacian with more detail in week 11 when we talk about segmentation. We show also the results in which various sharpening techniques are combined. So let us proceed with this very visual topic. We discuss next the use of special filters towards sharpening an image, which results in an enhanced image. This technique has been used for many years by the printing and publishing industry to sharpen images. So given an original image here, or original signal, we blur it, and this blurred version is the unsharp version of the signal. Subtracting it from the original image gives rise to the unsharp mask. Then this unsharp mask is added to the original image, resulting in the sharpened signal. As described in the previous slide, in the block diagram of the previous slide, if X is the original image, I blur it and I find what I denote here as the low frequency part of the image. I subtract it from the original and this gives rise to the mask, the unsharp mask. Then the next step is to add the unsharp mask. It's multiplied here by coefficient A, so it's multiplied by A and added to the original image, and this is the sharpened image. If I write the original image as simply the sum of the low frequency part of it plus the high frequency component of the image, then the previous equation looks like this. So with unsharp masking, I keep the low frequencies, but the high frequencies are boosted, multiplied by 1 plus A. And actually, if A is greater than 1, this is referred to as high boost filtering. If A is less than 1, then the mask is de-emphasized. So if we put this to practice, here's an image of these quarter coins, and this is the sharpened version of this image using this unsharp masking method. A equals 1 was used for this particular example. Here is another example of the application of unsharp masking to sharpening an image. Here is the original image, 216 by 308 pixels. Here is the blurred version of it by a 7 by 7 Gaussian. I subtract the blurred version from the original one and obtain the unsharp mask shown here. The unsharp mask is added to the original with alpha equals 1 to give this sharpened image, and with alpha equals 2 to give this sharpened image. So clearly the edges are sharpened, or the high frequencies in the image are boosted. The main idea behind these sharpening techniques is to add to the original image high frequency information, edge information. We saw that with unsharp masking, we found the unsharp mask the high frequencies by taking the difference between the original and the blurred version. Another way to obtain high-frequency information is by finding the derivatives of the image, and specifically finding the second derivative of an image, which is referred to as the Laplacian of the image. We're not going to get into any details at this point, since we'll study gradients and Laplacians, the first and the second derivative of an image, when we talk about segmentation. So for the time being, assuming that I can find the high frequencies through the second order derivatives, I can then add them to the original image and sharpen it that way. So here's an example of an image of the moon's north pole, and this image actually is a mosaic. It was put together by 18 images taken by Galileo's imaging system back in '92. So if we look at this image, it looks kind of blurry, and again, we would like to sharpen it. So if we find the second derivative of this image, the Laplacian, it looks like this. The Laplacian ranges from minus 255 to plus 255, assuming the original image is an 8-bit image. And what we see here is the positive values, since the values below 0 were clipped, were set to 0. Another way to show the Laplacian is by rescaling it, by scaling the minus 255 to 255 range, mapping it into 0 to 255, and then this is what we see. So clearly, the second derivative contains the edge information of the image. So if I add the Laplacian to the original image, then I obtain this image, and if we compare this sharpened to the original, it should be clear that indeed the edges are enhanced, the high frequencies are boosted. There are different ways, as we'll see, to compute the Laplacian. So if I compute it in a different way, by the way, for this example, the Laplacian was computed as shown here. And more specifically, this is like a two-dimensional impulse response, minus 4 in the middle, and then 1 here, 1 here, and 1 here. So this Laplacian was used to compute this here and to compute this image. So if I compute the Laplacian a different way, and the different way is shown here, so the impulse response now is minus 8 in the middle, and then 1 at all other locations in this 3x3 mask, then I obtain this result, which, by the way, is definitely sharper than the one I had with the first version of Laplacian. So this is the basic idea of sharpening. Take the original image here, add the high frequency information as conveyed here by the Laplacian, and then we have these beautiful results down here where you can see considerably more detail when it comes to edges of this image of the moon. We see here a combination of some of the sharpening and enhancement techniques that we have covered so far. So let's consider this whole body bone scan shown here. By looking at this, it looks rather blurry. So based on what we've learned, we can find the Laplacian, the second order derivative of this image. Then if we add the Laplacian to the original image we started with, we get the sharpened image as shown here. We can also take the first order derivative. It's called Sobel gradient, one of the ways to implement the first order derivative, and again we'll cover these in more detail when we talk about segmentation. Now I can take the Sobel, the first order derivative we just saw, and smooth it out. So it's averaged with a 5x5 filter. Then I take the product of the sharpened image that I had obtained by adding the Laplacian with this smoothed Sobel gradient. So this gives me a mask, their product. And then I can add this mask to the original image, and I obtain this sharpened image. And finally, I can use a power law transformation to further enhance the appearance of this image. So we do have various versions of enhancement, right? This is an enhanced version of this, and this is a sharpened version of the original, and so is this one a sharpened version of the original. So this also illustrates the fact that I've mentioned multiple times that when we talk about image enhancement, there is not just one specific objective that will give us the optimal way to enhance an image, but instead I have a set of tools in my bag that I can utilize them appropriately, and I can try different tools, and at the end I can choose the one processed image, enhanced image that is more suitable for my own purposes.